If you have any difficulties, that please let me know. I'll go through this 3 to 8 decoder. You may remember that previous one here with this one. We have these 3 inputs A, B, C. Because of that, we are having 3 inputs. We'll have 8 outputs. Starting from Y0, Y1, Y2, 6 and Y7. Okay. The truth table is also not a new one. Same pattern you can follow here also. This. You can see that for each and every input combination, one output line will be one at a time, like this. Okay. Here, this should be one. Now, what do you think that? How can we make this one? What is next step? We can write output equations for these lines. How many output equations will be there? 8 output equations will be there, starting from Y0. Okay. Then Y0 will be A bar, B bar, C bar, Y1, Y2, Y3. This one A bar, B bar, C bar. This one A bar, B bar, C, A bar, B, C bar, A bar, B, C. Here, like this. Now, these are the 8 equations we can write for these output lines. Then we can draw the diagram. Minimization is not possible. Then we can draw the diagram. Okay. I think you can try this drawing of this diagram. There is nothing new here. You know how to draw the diagrams. Okay. Then we discuss about and we tried this making 2 to 4 decoder. Next one, the 3 to 8 decoder. We did it halfway, and it's up to you to draw this diagram, because you know how to draw diagrams when you have output equations. It's a practice. Please try to do this one. You will not have any difficulties, but if you have any kind of difficulty, you can tell me next day also. But at least that 2 to 4 decoder, 3 to 8 decoder, you should know that how to make those things. Okay. Then this is the first one. The second one, 3 to 8 decoder. What will be the next expansion? Here you can see when you have two inputs, there are four input combinations, then output lines. How many? Four output lines will be there. Here, 3 input lines, then combinations are 2 to the power 3, 8 combinations. Then for these 8 input combinations, we have 8 output lines. Likewise, that the next expansion will be 4 to how many? It will be 4 to 16 decode. Okay, next one, 5 to 32 decode. Okay, then what do you think that? Likewise, we can go 8 to 256 decoder, then 10 to 1024 decoder. What do you think this one? 1024 output lines, 10 input lines. Then altogether, the device is having 1034 input output line. What do you think? Are these type of devices practical? And some of this, here we have 1034 lines. The other way, if you go, maybe if you have 20 input lines, 20 to 1 million output lines. And if you go a little bit beyond this one, then if you say 30 to 1 billion decode. You can write like this, but what do you think? Is it practical to have this type of devices having this many number of output lines and input lines? Actually, here, all of you have computers. You may have desktop computers, you may have laptop computers, and whatever the computers you may have. Then it seems that when you look at these diagrams, then you look at these figures, we can imagine that these type of devices are practical. But when you look at your computer, when you check your configuration of the computer, most probably your computers are having memories, RAMs. These days that any ordinary computer, they might have 2 GB, 4 GB, and 8 GB type of RAMs. But assume that if your computer is having 1 kilobyte of memory, if it is 1 kilobyte, 1 kilobyte means 1024 bytes. Okay. See this one. Here we actually in our computers we have 2 GB, 4 GB, 8 GB, huge amount of memories we have. But for the moment, assume that you have 1 kilobyte of 1024 bytes. To make this 1024 byte memory chip, we need 10 to 1024 decode. Okay. Then see then 10 to 1024 decoder, we need that when you have 1 kilobyte. If you have 1 megabyte of memory, how many one? This one, it should be 20 to 1 million decoder we need. But in your case, your computers, you have 1 megabyte is nothing. You have more than 1 GB. It's 2 GB, 4 GB, 16 GB, like that. 32 GB like that you will have. Then you need, really you need this 32 1 GB decoder, 36 to 64 GB decoder like that. You need this huge decoder. And don't underestimate about this one. And sometimes it might not believe, unbelievable, these figures. But anyway, these circuits are these ones are practical. Okay, that's what about, okay, we can, at least that you should know that how to design this 2 to 4 decoder and 3 to 8 decoder like this. But when I say decoders, when I start about these decoders, I mentioned these are standard decoders. Then what about non-standard decoder? What is that? Where can we find non-standard decoder? What is the difference between the standard decoder and non-standard decoder? Okay. What do you think? And this is 3 to 8 decoder. You don't know that it suddenly closed. Now you can see, I think. Okay, if you can't see these diagrams, and can you please let me know? Okay, when we have the non-standard decoders, actually, what is the difference between the standard decoders and non-standard decoders? You may remember that how we do for this standard decode. This is a standard 3 to 8, 2 to 4 decode like that. We have those things. Okay, I'll copy this one. I'll copy the previous notes. And this is 2 to 4 decode. But this is standard. This one is standard. This is standard 2 to 4 decode. Okay. Then what is the difference between the standard 2 to 4 decoder and non-standard decoder? Now this is 2 to 4 standard decoder truth table. Okay, for the moment, like that here. assume that in this case, these type of ones may be there, but there may be certain requirement to make this one, but the previous pattern was gone. Okay, that pattern is not there, but anyway, we will have a certain device having 2 input lines, having 4 output lines, and this is the truth table we want. Okay, based on that, if you write output equations, okay, if we write output equation based on this one, okay, here A bar B bar plus A bar B. Y1 is A bar B plus AB bar. Y2, this is A bar B bar plus A B bar. Okay, then Y3, here we have 3 terms, A bar B bar plus A bar B plus AB. Okay, then shall we minimize this one? This is when we take A bar out, inside we have B, only B plus B bar, that is 1. Here A bar B plus AB bar, it's A exclusive O. This one we can take B bar out, then it is B bar. So Okay, sorry for the delay. The slight impact was not working. Now it's okay. I think yes, we can minimize this one. Then here this is A bar plus B. Likewise, we can minimize this one. Okay. Then after minimizing this one, we can draw the circuit. Then whatever the way, this one is, we started this one is from the standard decoder, but this is a kind of non-standard decoder. Why do we say this is a non-standard decoder? Because it does not follow the standard truth table. We have some kind of deviations from the standard decoder truth table, then we say this is a non-standard decoder. But after that, the rest of the designing process is same. We can write output equations, but here we can do minimization if possible. We can do the minimization. Then for this minimize equations, we can draw the circuit. Then this is a kind of non-standard decoder. But there are certain non-standard decoders. We can see sometimes that we can see. Decimal to, sorry, the other way. Binary to decimal decode is one non-standard decode. Binary to decimal decode. Most of the time you can see the function name is there. Function name will be there. Here, in the previous case, is a 2 to 4 decode. You have 2 inputs and 4 output lines. Then we take this number of inputs and number of outputs to name the decode. Otherwise, that if it is non-standard decoder, then we can take the function. What type of functions we are expecting from this one? Binary to decimal decoder. Sometimes that we can see binary to gray code decoder. Then this is binary to gray decoder. Likewise, we can see there are many type of non-standard decoders available. Okay, here we are going to discuss today one additional non-standard decoder. We have real advantage of using this one. We need some kind of special non-standard decoders to do certain activities. But here today we are going to discuss another non-standard decoder. Here you know that the meaning of this non-standard decoder is something like this. If there is a deviation from the standard decoder, if there is a deviation, we can say it's a non-standard decoder like this. But anyway, these are the ready-made non-standard decoders, readily available non-standard decoders, and some other non-standard decoder we can discuss here. Have you seen this type of displays? This type of displays to show the numbers. We can make numbers by turning on the several segments of this display. Okay. It's a kind of display like this. And here we have some kind of naming convention here also. We can name these segments, this simple A, B, C, D, E, F, G. then we can use these type of displays. We say this is a 7-segment display. Why is a 7-segment display? We have 7 segments here. Using these 7 segments, we can make any number. For example, if you turn on B and C segments, it will be number 1. During that time, all other segments will be turned off. Okay, if you want to make number 3, then A, B, G, C, D. And when you turn on these segments, then we can show number 3 here. Likewise, we can make, then we say these are the 7-segment displays. Displays. Then we have 7 inputs here. Then when we give certain voltage here, the relevant segment can be turned on. Okay. Then assume that you have a circuit, some circuit, it's generating numbers. Okay. Certain circuit is here, and this circuit is generating numbers. And assume that these lines, output lines are A, B, C, D, like that. And if you look at these values, all these values coming from digital circuit is their binary values. But when you show binary numbers to ordinary people, even for us also, it does not make sense to us. Easily we cannot identify the number. What type of number it's showing, we cannot identify those things. Okay, then how can we make a circuit? How can we use this type of 7-segment display here? Now we have this type of segment here. We have these 7 inputs also. We can use these type of 7-segment displays to show numbers. When we turn on the relevant segments, we can show the number on the display. But here we have another digital circuit. This circuit is generating certain numbers. Sometimes it may be a calculator, whatever it is. Sometimes it shows the time value, and it shows sometimes it may be unit counter. The people who are going through a door, we can count the number of people going through the door. Then we can use this type of display to show the number. Like that, we have a lot of activities. But here, the problem here is that we have 7 inputs here to turn on the relevant segments. But when you look at this one, this gives us the binary numbers. For example, we have this DC, BA, and if it is 0, 0, 0, 0, what is this number? It's 0. What is the maximum number it can use? It can give. This is 50. But when we have this one, this is 8. This is 9. Okay, beyond 9, we cannot display these values on this display. But anyway, from 0 to 9, we can generate these numbers and we can show those numbers on this 7 segment display. But the problem here is that in this circuit, we have 4 output lines. Here we have 7 input lines. How can we match this 4 to 7? This 4 output lines and the 7 input lines, how can we combine? Then for that purpose, okay, for that one, we can have this type of device in between these two. Okay. Then it can take these inputs from the binary circuit like this, and it can generate the output lines, which 7 segment display can understand. Okay, those values, the converted values will be understood by the 7 segment display. Then for the moment, we can say, we can give a number to, we can give a name to this one. This will be, here this side we have binary. This will generate binary. You can say this is binary 2. This is binary 2. 7 segment decoder. It's a kind of decoder, but you know that this is a non-standard decoder. Another example for non-standard decoders. Why? We have, this is the decoder we want to design, but this is non-standard decoder. Why? If it is standard decoder, this will be 4 to 16, but here we have 4 input lines and 7 output lines. Then it will be 4 to 7 decoder, something like that we don't have. But we can say it's a non-standard decoder. The decoder, we can give a name considering the functionality of that decoder. Then we can say for the moment binary to 7 segment decoder. Okay. Then shall we prepare truth table for this one? We have these inputs DC, BA. This is the input side. Starting from 0, 0, 0, 0, we can go. And the other side, we have the simple A, B, C, D, E, F, G. The segments. Okay. 0, 0, 0. For example, this is 0, 0, 0. 0, 0, 0 means the number we want to show on the display is 0. To show 0 on the display, you can see here. What are the segments we can turn on? We have to turn. Other than G, all other segments should be turned on. Okay. Then we say G should be 0. All other segments are on. Okay. Then what is the next number? It's 0, 0, 0, 0, 1. 1 means decimal number 1. Then how can we show number 1 there? Then BC should be 1, 1. All other lines will be 0. Isn't it? To show number 1, you can turn on B and C segments, and all other segments you can turn off. Okay, then likewise said, can you fill this table? The next number will be 2. 2 means 0, 0, 1, 0. Then 0, 0, 1, 1 is 3. 0, 1, 0, 0, it's 4. 0, 1, 0, 1, it's 5. 0, 1, then it's 6. It's 4. Okay. Then next will be 7. And this is 8. And this is 9. And this is 10. Seven, 8, 9, 10. Can you fill the truth table here? After 10, what can we do? We don't have anything after 10. We cannot display anything after 10 for the moment, but there are certain designs, there are certain solutions different manufacturers have bought up, but we don't take all these things. And for the moment, we say after 9, these displays are not working. Okay, then 10, 11 like that, but the binary pattern doesn't stop here. It's 11, 12, 13, 14, 15. 15 means 1, 1, 1, 1. Okay. If you want, you can fill this one 1, 0, 1, 1. Then this is 1, 1, 0, 0. This 1, 1, 0, 1. This is 1, 1, 1, 0. But up to 9, we can do whatever the number we can show here up to this one. Can you fill this truth table? to show number 2 here. Then number 2 will be FC. Other than FC, then we have to turn on all the segments. Okay, for 3, EF should be 0. For ADE, ADE 5, BE, B and E should be 0. Others are 1. 6, only B should be 0. Then 7, D, E, F, G. 8 all. 9, E should be 0. Beyond that, we can't do anything else. But different manufacturers have different solutions. But for the simplicity, we are not going to address all these things. You can put whatever the value here. If you want that, you can turn on entire display, giving zeros here. Giving for all the combinations, you can put zeros here. Then the entire display will be turned on during this part. Okay, if you put zeros here. Okay. Otherwise, that you can put the different number, it doesn't matter, but different solutions you can take. And sometimes that if you know that your system, this circuit will not generate numbers beyond 9, you can put X here, don't care states here. Likewise, you can have the different solution for this one. For the moment, we will stick to this one. Then after that, what we have to do is that we have to write output equation for simple A, simple B, C, like that, up to G. You can write output equations. Then we can try to solve this one. But practically, we don't do this one. We should know how to do the design, but practically we are not going to design all these things in a lab or in a practical way, because all these circuits all these modules are readily available in the market. It may be these days, I don't know the actual figures, the values, but a couple of months ago, it may be less than 200 rupees. Okay. Then it's not necessary to make these ones, but we should know how to design this one. But one important thing should be identified here. What is that? We can't go beyond this 9. That is the problem. Okay. Up to 9 we can show on the display, but beyond 9 we cannot do anything. But if you consider all these patterns 0, 0, 0 to 1, 1, 1, 1, starting from 0 to 15, this is pure binary. Altogether we have 16 patterns from 0, 0, 0 to 1, 1, 1. Here we have 16 patterns. But from these 16 patterns, we don't consider this the last 6 patterns. Because of that, this is not pure binary. If it is pure binary, we have to consider all the combinations. But here we consider only 10 combinations. Then because of that, we can't say this is binary to this 7-segment decoder. Instead of that one, we can say here, this is BCD, binary coded decimal to 7-segment decoder. Why? Here we have binary values, but we coded those things into decimal. Okay, because of that, those values are not pure binary values. We say it's binary coded decimal. Then this converter is, this decoder is BCD to 7-segment decoder. This is BCD to seven-segment decoder. Okay, then how can we, why do we need this type of decoders? Shall we try to understand this one? These are the decoders, the standard decoders are there, but not only the standard decoders, depending on the different requirements, we have non-standard decoders also. Non-standard decoder is not a difficult thing, it's not a magic. It's a kind of another type of circuit, it's another combination circuit. And for these ones also we have truth table. If you know the truth table, it's not difficult to design this one. You can write output the equations and you can minimize those equations. Then after that you can you can draw the circuit. Okay, but several standard identified non-standard decoders are also available. Classic examples are binary decimal decoder, binary to gray decoder. Likewise, that we have different type of non-standard decoders depending on the job, depending on the functionality they are providing. Okay. Then one type of that type of decoder is a BCD to 7-segment decoder. But here we can identify the 7-segment display. 7-segment display is a type of display. It is having 7 segments and turning on several segments at a time. We can show the numbers on the display. Okay. But anyway, that to drive that display, to turn on the relevant input values, the input lines, we need another kind of circuit here. Why? Because that binary circuits are not directly compatible with 7-segment decoder input lines. Then binary circuits are providing binary values here, like here the ABCD. Then they will provide these numbers, but these numbers are having a compatibility issue. This display, 7-segment decoder display, and these binary circuits are not having direct compatibility. Direct connections are not there. Then we make a different circuit, a separate circuit to combine these two. The function of this intermediate circuit is a decoding function. But what type of decoder it should be? It takes a kind of binary inputs to its input side, and it generates, when the relevant binary pattern comes, it will generate the necessary number pattern on the other side. Then for that particular input combination, the particular input one, the output circuit will take this one. The output circuit will, this decoder circuit will generate these type of patterns. Then this pattern, when we combine these patterns to 7-segment display, then we can show all the numbers generating from this circuit. We can show all these numbers on a 7-segment display. But one restriction is here. That restriction is that when you consider DCBA 4-bit binary number, okay, its minimum value is 0, 0, 0, 0, that is 0. Its maximum value is 1, 1, 1, 1, that is 15. Then 0 to 15, 16 different combinations are there. But for this display, unfortunately, we cannot show all the values. Instead, that we show only the decimal number parts. Then when we say, when we take only the first 10 patterns and we don't care about the last 6 patterns, then we can't say it's a pure binary convert. So that the entire binary spectrum of 4-bit entire binary spectrum is not taken. Because of that, we say it's a different type of things. Then it's here we have binary values, but we show these binary values on a decimal display. Then we can say this is binary coded to this. This is BCD to 7-segment decoder. We finally can. Okay, then any question regarding this one? Here also that if you want, then I can write some equation here. This is okay. First one. Three and another 5 should be there. Okay, this will be equation for simple A, and we can minimize this one. Then we can have minimize the equation, but it is not necessary to do this way. But you should know the method of designing of this one. Okay. After that, you can write all 7 output equations starting from simple A to simple G. Then you can do the circuit. Okay, anything, any question? Okay, anything, any question? Okay, then if you don't have any question, then we can move into the next section. Then from any of these things, do you have any question? These are the special type of decoders, non-standard decoders, and this is another very useful non-standard decoder. Okay. Then any question, anything? Okay, then we can move into next section, next lesson. That is sequential circuits. So far we have discussed about combinational circuits. In sequential circuits, different type of circuits. So far we haven't discussed, haven't designed, haven't made these type of circuits. But these are the essential type of another essential type of circuits in digital electronics, because whatever the circuits that so far we have discussed, we didn't see memory action. There is no possibility to store previous numbers with the circuit so far we have discussed. Okay. Then what do you think about them? Have you seen memories in our problems, in our designs? No. Memory are most important type of devices in digital circuits. But here with combinational circuits, we can't make memories. Instead, we need sequential circuits to make memories. But when we make sequential circuits, we have a different type of building blocks here, the sequential circuits. And sequential circuits building blocks are flip-flops. Flip-flops. Actually, here we are going to discuss three type of flip-flops. This RS latch, second JK flip-flop, and third one D-type flip-flop. Okay, these are the basic building blocks of sequential circuits. Then we have to understand the operation of these flip-flops. Then we can discuss about flip-flop applications. Okay. Then first we take RS latch. And here we have two input lines, then R and S. These are two input lines, and these are the output lines. But physically, we have two output lines, but we say is a single output line. Why? Q is a non-complementary output. Q bar is the complementary output. Q bar is the same output, but both forms are available at the same time. You can see here, with this sequential circuits, there is a feedback from input to output, output to input, like that. These are the this is the difference between the sequential circuit and the combination circuit. With the combination circuits, we didn't have this output to input feedback loop, but here we have output to input feedback loop. With this concept, we are making memories, and we are to memorize something. We need what we had a moment ago. Moment ago, output will be taken into the input side. Likewise, that we will have some kind of memory action here. But anyway, we'll discuss all these things here. Then this side you can see this is reset input and this is set in. That's why this SNS, RNS values are here. Okay. Then can you try to write this Q output value in terms of RNS? Because here you know that these are no gates. You know how to write no function. Okay, to write no function here, you need these two input values. This one is R, the other one is Q bar. It's no. Here, then we need Q bar. Shall we try to find Q bar? What it is? Q bar is S plus this one, S plus Q. But when look, you can see when you write equation, Q bar is there. When you write equation for Q bar, Q is there. You can see that the input to output, there is a connection between input to output. That's why we say it's a feedback loop. We have directly connected input to output like. Okay, then we should know the truth table of this one. Then before we write the truth table, we should understand one thing here. And here, determine the output value. We have to consider time. For example, assume that here you have Q. But after that, after this Q, you can change some RNS values. Then you will have new Q. Before you have new Q now, the moment ago, you had previous Q. Because of that, in this timeline, we have same output line, but output values may be different. Because of that, we say in this timeline, the different values may be there. This one, this is present now. But this is, if this is present output, this one is previous output. And this one, this will be next out. Okay. Then it's not a big thing, it's not a difficult thing, just a timeline notation. just a notation to show that the difference between the present, previous, and next output levels. And here we put this one will be Q plus. Okay, and this is Q and this is Q plus. Next one will be Q plus plus. Okay, then we can make a truth table. We can write out truth table here. This is R and S. And we write values for only Q. Then if you know Q, definitely we know Q bar also. Then we write output values for this is Q plus 0, 0, 0, 1, 1, 0, and 1, 1. Then what is the meaning of this one here? Here R is 0. R, what is R? R means reset. S means set. Set and reset. What does it mean that when you say to set something? The general meaning of this, general idea of this one, setting output value means output will be 1. Here we ask to reset and not to set. Okay. Resetting means output will be 0. But here we don't ask to reset, we don't ask to set. Then what will be there? We are not asking to set. We are not asking to set means we are not going to change output to 1. We are not asking to reset. Then we are not going to change it to 0. Actually, we don't do anything now. Why? We don't want to do anything here. But here we want to set, then output will be 1. Here we want to reset, output will be 0. Here we don't do anything means we'll have the previous one. This is previous out. And this is output will be set. This is output will be reset. What about this one? 1, 1. We are asking at the same time, we are asking to set and to reset. Is it possible? No. Because of that, this is illegal. Okay. It's forbidden. We should not do this. Okay. And okay, but with this truth table, you can see this RS flip-flop, we have only 2 inputs. Having 2 inputs means we have only 4 combinations, but even having 4 combinations also, we cannot use 1 combination. Last combination we cannot use. Okay. Then we can, hereafter we don't draw all these internal diagrams there. Instead of that one, we draw this RS flip-flop, actually RS latch, like this. This is R, S, Q, Q. Okay, now this is the RS latch, and we will discuss JK flip-flop and D-type flip-flop next day. Do you have any question? If you don't have any question now, we can stop the class, and we'll meet next Sunday. Okay, thank you very much for your participation, and thank you very much for your time, and have a good week.
Thank you, sir.